Alpha, beta, gamma, delta? We good? Okay. Yes, question.
Related to the homework questions, there was also an issue of the circled diagrams in certain functional groups. It wasn't clear whether you were asking whether it was a ketone or, not a ketone, yes, ketone, or a carbonyl group, because what was circled was just a carbonyl, but the answer was looking for was ketone. So
but there was a ketone, so there was an oxygen adjacent to it,
right,
is what you're saying. So that would have made it a ketone. Okay. Yeah, I see how that could be confusing. Okay, so we can give you 3 points back. So, yes?
I think also for like number one, we were told to look up the value of something online for us to get the atomic radius. And a lot of the, like if you Googled it, it gave you the van der Waals reading.
Oh, yeah, so you
but then I used the atomic radius.
when I had them graded, I said as long as it was roughly on par with that. Yeah, so your number may not have matched the key. But what I used for the key was what I gave in class. So I presented a table that clearly listed all of the atomic radii. So, but when I had them graded, I told them to, as long as it was roughly in par there. Okay. And then there was one that was just wrong. Which one was it, Fong? Was it carbon bromine? That was the key was just wrong. So on this one, the electronegativity difference, I think that's what the question was asking. There was a table in the book and you were just looking for that difference. And if it was like larger than 0.3, then it was strong. And if it was less than 0.3, it was weak. So anyway, 0.5. Okay. Because carbon nitrogen is 0.5, right? Per that table. So anyway, there was one that was just straight up wrong, but everyone did fine on that. So, so we'll adjust that for those few points that were wrong. Also on the syllabus, on the syllabus I said to read Wade, which is an organic chemistry book for molecular orbital theory. And that's helpful, but I would also definitely go back and look at both of these chapters, including Atkins, because as I've gone back through it a second time, it's actually really good. So those are both, the first two chapters in your readers are what those are for valence shell. Okay? This was something I found that I thought was really good for thinking about quantum numbers and for listing the first, that game where we did for ruthenium, of listing the 4 quantum numbers. So again, we've identified several exceptions to when this is not the case, but this is going to clearly, this lists very clearly how you would find the first 4 quantum numbers, right? So if it was, what did we decide that it's 1, 2, 3, 4, 5, 6 is copper, is that right? So this would be, the first quantum number would be 3. And then the second one, D is L is 2. And then -2 because it's 1, 2, 3, 4, 5, 1. And then at that point, it becomes a -1/2 spin. Okay, because you've started at that point to pair up. Okay? So I'm just listing that because I found it after the fact. Okay. Yes?
So like for this and also for homeworks, right?
Yep.
I'll ask you to name like the 4 quantum numbers. You always want to like get the last electron, like the corresponding one.
If it's paired, yeah, so the very last electron you put in, right? So if this is the last one you put in, that would be -1/2. Okay. Okay. So last time we talked all the time about wave functions, and we had ended briefly on nodes. And just to touch a little bit more on nodes, that a node is where there is essentially 0 probability of finding an electron, and that's where it changes sign. And so if you think about a p orbital, and we tend to draw it, and sometimes they're shaded. So this is the node where there's essentially 0 probability and where it changes from shaded, as we're drawing it, shaded to non-shaded. So the change in sign. And yes, and we also talked about how a wave function is a component of the radial function and the angular function. Yes?
This might be an error of thinking of an electron candidly, but if we're considering, say, a px orbital, like
Yep.
what you do here, how would the electron get from one lobe to the other as zero probability?
It's magic because it's a wave, not a particle. Yeah.
Is there like destructive interference occurring outside?
That's what hybrid orbitals are all about. And so that's what we're going to talk today is when you get constructive and destructive interference. So that's what an sp3 orbital is, right? It's all constructive and destructive interference. Yep. So when either the radial, and remember we described the radial function as the just distance from the center, and then the angular function as the area over the curved surface of that sphere. When either of those are 0, then you have a node. So if we look at just a simple 1s, 2s, and 3s, a 1s has 0 nodes, a 2s has 1, and a 3s has 2, right? What's this right here? That peak. Which is, what would it be in terms of the x-axis? The Bohr radius, right? So that's a sub naught 0.53 angstroms, right? Is right there, okay? And so the 2s and the 3s have a node that's roughly twice that. And we looked at that a little more carefully, right? We looked at the 2s orbital, and we said that when r was 2a, the Bohr radius would cancel, and that would become 0, right? For a 2s orbital, this is the radial function for a 2s orbital. When r is twice the Bohr radius, that term becomes 0, right? And that's what this is showing graphically, that this is roughly twice as far from the axis as that peak, okay? So similar, the 3s orbital then has another node farther out, okay? Okay. Yes, and this is saying that again, the angular functions will also can produce nodes, and so what you could do is set these equal to 0 and solve for r when there is an r, and determine where there's a node. Yes.
So what's the difference between the left-hand side where it says
Okay, so this is, let me pull that up to give you a better explanation. Is this the best I have? No, I guess I don't have anything better than that. So one of them describes theta and one of them describes phi, okay? So each of those subcomponent functions is for theta or phi. And this is when they're multiplied by each other, okay? So this is the theta and phi function, and this is when they're separated. Make sense? Then this one is in Cartesian coordinates as opposed to spherical coordinates, okay? This I thought was really neat. This is one of the wonders of Wikipedia, where they correlated the first 3 quantum numbers to the number of nodes, right? Isn't that beautiful? I want this in my office now. So so this is what? What kind of orbital? S. So it's a 4s orbital, and it has 1, 2, 3 nodes, right? This is a, what's that? So this is a 2p orbital. This one starts to become a little, the third one starts to become a little arbitrary when you show it in, well, not arbitrary, but it's difficult to show it in 3 dimensions. Yeah?
How can you tell there's a node? When it gets dark?
When it's dark, right? Because a high chance of electron probability, low chance of electron probability. So if there's 0 chance, you've definitely got a node, okay? How many nodes are in this one? It is 2. You could kind of argue like, well, there's only technically 1 there, right? But there are 2 because there's 2 different planes through there, okay? No, because there's no, like you're talking about out here.
No, inside of that, in between there's like 2. So there's like the X and then there's like a circle. Yeah.
You're talking here? I don't think that's, I don't think those ever go completely to 0.
Oh, okay.
Yeah, that's just low. Yeah.
How do you determine from this which is an angular node and another one?
That's a good question. So these are clearly which ones? Those are clearly radial. If it's an angular node, it's a function of shape, right? And if it's radial, it's a function of distance. So these, like this one is going to have, this is a 3p, right? So no, a 3d. So it's going to have 1 radial node, I think. Where's my cheat sheet? No, 3D is 0 radial nodes and 2 and. Oh, thank you. That is a P. Yes. Okay, so then it has 1 radial node. Yeah. Yeah.
Could you advise us on a resource where we could see these plots in 3 dimensions?
Yeah, I can send that out. Yeah, we had that one earlier at the very beginning. It's hard to see them rotating. Let me see what I can find. Yeah. Okay. So do you think you could work backwards then? Like if I showed you, if I just showed you that, that would almost be impossible because you wouldn't know. What wouldn't you know here?
You know this is pure.
You know that.
Would it be hard to know what its principal number is?
The principal would be hard, right? The 3 would be hard. And this would be difficult too.
It's an actual.
What's that?
So if you didn't know the principal number, you'd tell to find that.
Yeah, I mean, the S's are particularly easy, right? And the D's start to become easy, but when this is a D and this is a D, right? That's tough, right? When I first saw this, I was like, this is a great test question. And then I was like, nope, there's too many places where you could mess it up, where there's too many. So yeah, we can't do that. So this is a really helpful resource that like just straight up tells you. This is just solving those equations, right? Where these are the number of nodes. And this is showing in a slightly different way how that one has 2 nodes, right? And how it never completely goes to 0 out there. Okay. If you really want to convince yourself, you can sit down and set all of those equations equal to 0 and solve them. I mean, that's the easiest way to do it, right? So, okay. On to bonding. So we talked about Lewis dots, and then this is going to be today, and molecular orbital theory is going to be tomorrow. I'm just going to assume that you guys are relatively comfortable with this. I don't imagine testing over this, but I think you should, if you start to look at your Lewis dot structure, you would know a little bit more about what the shape would be. Okay, So valence bond theory was developed by Linus Pauling in the 1930s, and it was the first attempt to to use quantum mechanics and quantum theory to explain the covalent bond. Has anybody seen Linus Pauling's book on the nature of the chemical bond? It's huge. It's beautiful. What's that?
Is it as big as a textbook for this class?
Oh yeah, no, it's not as big as that monstrosity. So what we're doing here is talking about the wave function as the nature of the chemical bond. Okay, so if we start as we always do with our simplest model of hydrogen. Okay, so there's a wave function for each of these, right? And it's a 1s. And if we look at it this way, we could think about it in this respect, right? 1s. Okay. But as these become superimposed, there's this region where the electrons essentially start to overlap, okay? And this is our constructive interference, right? And so we could write this then. So at this point, the electron, when we're in a situation like this guy's electron is this guy's electron, and this guy's electron is that atom's electron, right? These, when you start to form and superimpose these wave functions, it no longer becomes clear which electron goes to which atom, right? So the right way to start to write this wave function is that this term is written a lot of different ways. Your book writes it as a chi. Most of the other resources write it as a phi. This is confusing. I hate when this happens in science. And then you could also write it as just another phi, right? As like a component phi, okay? Do you want to make a consensus and stick to one thing, or do you want? I mean, obviously we do. What do you guys want to use? Want to stay with phi? Okay. So what this is just saying then is that this is a subcomponent of this other wave function. This is a wave function, right? And this is also a wave function. Okay? It's just that this wave function is the superimposition of these other two. Okay? So what this then is the wave function of A. And these represent the electron. So electron from 1 or electron from so we can call this A and electron 1. This is B, electron 2, right? But because of this situation where they're superimposed, we also have to consider when 2 is on 1 or 2 is on A and electron 1 is on B, right? Okay. Okay. If we think about it in terms of our spins, basically, what happens here is that these become matched in what's known as a sigma bond. Okay? And this is at lower energy because your spins are now matched, right? This is a more energetically favorable situation. Okay? Note also that let's start up high. The number of orbitals is conserved. Right? So we started out with 2 orbitals, and we still have 2 orbitals. This is a sigma bond. and it's known as a bonding orbital. Okay? This has a star here because this is known as an antibonding orbital. Okay?
Is that always above the previous orbitals? Or they were-
An antibonding orbital, yes. Yes.
So spatially on our superimposition of the two S approaches here, we see the antibonding opposite this space.
That's right. Yeah. And so if you did like the, so what does this sigma bond then start to look like? If these are your two, it's essentially something like that for your bonding orbital, whereas your antibonding would be something like that, right? Sigma, sigma star. Yes?
If it were like something other than hydrogen and it was more complicated, do you expect us to align the S and P and D according to their energy levels?
This theory really only works for beryllium through fluorine. So it's rare that we don't get Ds into this orbital. But yes, this is hinting at molecular orbital theory, and we'll get into these more on Wednesday in terms of constructing these kind of diagrams. Okay. So yes, and so therefore the H2 is energetically favorable. This is a spontaneous process. The other issue is that you have increased electrostatic interactions, right? Because now each electron can feel 2 protons as opposed to just 1. There's increased electrostatic stability there. Okay. So therefore, this is kind of like those Lennart-Jones plots that we talked about briefly, where if this is our intermolecular distance, so this is the H to H distance, right? We see this familiar shape. Where this characterizes the strength of the bond. Okay, we saw that before. What I forgot to mention when we talked about these is what that characterizes. What do you think that? So, as opposed to maybe something that looked like what can the white one do that the pink one can't? Or what can it do more? Stretch, right? It has more stretching. This is a less rigid bond. Okay. Yeah.
How do you know what height to take that at?
Height to take this at?
Like the width, like because the width will change as you go up and down the ground.
I mean, this is technically, how do you get it? Through spectroscopy, right? Like experimentally, you get it from spectroscopy.
Is it measuring like the maximum width, or like what exact width is it? Because if you scale it up and down, you'll get a different width of the.
You mean scale this up and down?
Like the horizontal one, the horizontal line that you're saying is the stretchability of it.
Yeah.
So you-
Oh, you're saying where would you draw it? Like here versus here? I mean, probably the full width at half max is what, yeah. Okay. What would this look like if this was an ionic bond? What would the wave function look like if it was an ionic bond?
Just have like a single, like, say, BA with both 1 and 2 in it. And you would not have electrons.
And 2 would not have any electrons?
Not having any
There's
electrons.
still some like
It's fully shared.
Yeah, yeah, so it would be where A has both,
Yeah.
or B has both. That should be, yeah, that is a plus. Okay, and it's entirely possible that this could go to 0, right? That B, if it was a very, very ionic bond, that B would go to 0. And I didn't label this, right? So this is covalent ionic. And believe it or not, people study this intensely enough, and covalent, and there's a term lambda that scales the ionic component. So in real life, when you study this for years and years and years, you find that there is some ionic nature to a hydrogen bond, to H2. Isn't that amazing? The lambda is 0.06. So it's about 6% ionic character. That's neither here nor there, but it's kind of interesting, right? Okay. So what about a slightly more complex model? What if instead of H2 we had N2? Okay, so each N is going to have a 1s, which we know. Are those going to be involved or bonding? Not really, right? But we do have a 2s that has 2. Here's our other atom, so N of A, nitrogen B. This is our 2s, and then our 2p, each has 1, 2, 3. Okay. So these, where can we do our binding, right? These are unpaired electrons that are keen to do binding, right? So similar to this, we're going to get, if this is N of A, N of B, we're going to get superimposition of, what do you think, one of our p orbitals, right? Okay, and we have other p orbitals that are here, and then I'm going to draw it kind of like that. And frankly, let's see if I just have a better version.
So why doesn't this theory work well for bigger elements?
Probably because the electrons just don't obey. They're less structured. When you get to those higher order elements, the rules of staying in one orbital fall apart more readily.
And so this theory, pretty much, like this theory mostly functions for like modeling one electron systems.
No. I mean, it works well for all carbon-based materials, right? So for all of organic chemistry, it works pretty darn well. Yeah. But if we wanted to use this for like a titanium macrocycle, it starts to fall apart there, just because titanium's orbitals can move around so much. Okay. So, yes. So in this situation, right, this is again going to form a sigma bond, these 2p z orbitals. By convention, the p is frequently drawn at, or I'm sorry, the z is frequently drawn as the interatomic radius. Is that how they did it? Yeah, they did. And so then you have one as x and one as y, 2py, 2px. Okay? If you want to ask yourself, is it a sigma bond or a pi bond? The answer is, if you rotate it, is there angular momentum around the interatomic axis, right? So if we rotate it here, there's no momentum for these two. It's a completely mirrored image, right? In these situations, because these lobes are not symmetrical, you would have angular momentum. Okay? Let's see if I phrased it slightly better on my slide. Symmetrical with respect to the rotation of the bond. Yes. So note that you can also get sigma bond. Yeah, so here we're getting a sigma bond from two p's, right? Sigmas aren't restricted to s orbitals. Okay? And then this, our 2px or 2py, are going to form what is known as pi bonds. Okay. And pi bonds are a weaker bond because there's less overlap with the component p orbitals relative to the sigma bonds. Okay? Does that make sense, right? This bond looks pretty similar to the original p orbitals, right? It's gonna when it morphs, it'll look something like that, which is quite similar. But the difference between the component px and py is pretty different than the pi bond. Okay? Okay. What if we did? Yes.
So the top part is the sigma bond, you said?
The top part is this is the sigma bond, and then these are two pi bonds. Yeah. So this would then look like a sigma bond and then two pi's. If you want to look at it different, here's acetylene. So acetylene's also a triple bond, right? So one sigma and two pi bonds. Yeah.
So where's the symmetry? Is it down the middle? Or
No,
is it along
this plane.
Exactly.
Yeah.
And for the top p orbitals, where are you measuring the symmetry that it is not symmetrical?
Still through here.
Still through there.
Right? So if you rotated it, the purple would replace the orange, right? Okay. Let's get back. What would this look like as in terms of the wave function? You're going to have, what about the 2p, what about this pi bond? It's going to be very similar to what we had before, right? 2px of A, 1 phi 2px of B, 2 plus 2px of A, 2px of B, 1. Okay? That's the component wave functions. Ditto for y. Okay. We're going to come back to that in a minute. Yeah?
Is there a reason, is it because of local normality that the 2 pi y and 2 pi x don't usually form bonds?
That the 2 pi,
The 2p, I mean, don't form like pi or sigma bonds. The 2px and 2py.
So that's, again, it's a convention. They could, right? It's just that we're calling this distance between here z. So the question was, why don't the x and y, and they would, right? Okay, so let's look at an example where they do form a bond, right? So what if we looked at methane? So what if we had CH4? So here you've got 2s, 2p, right? And for hydrogen, you have 1 electron times 4. Okay? So in this situation, what do you have available for bonding? I mean, you would say, well, I've got 1, 2, 3. But you all know that carbon always forms 4 bonds, right? And you probably then know that this forms what's known as an sp3 hybrid orbital. Okay? Because it involves 1 s orbital and 3 p orbitals. Okay? So it's a hybrid orbital. Okay? So, you know, this, so what does this look like then in its wave function? I'm just going to write it down and then, well, actually, do I have it on the screen? That might save time. I don't. So you're going to have right? Every one of those is completely the same energy, right? But they're not coming from the same p, x, y, and z's, right? This is x, y, z. Okay? So the way these components, so if we call this bond A, B, C, and D, which is completely arbitrary, of the S I'm just going to write S. Technically, it's the 2S of the 2P, right? So this is the PX plus PY plus there's going to be 4 of these, right? S is always going to be positive, right? Because it doesn't have, at least the 2S doesn't have any nodes, right? The second one is going to be negative. Now we go positive here and negative here. Might be inconsistent, kind of not. And then the last one, S is still positive, and now X is positive again, and then these 2 are negative. Why does it have to be this way? These are all for an sp3 hybridized system, and it doesn't matter, like it could be methane or it could be some really long molecule like this where you've got whatever. These are the wave functions.
When you multiply with 2 of them, do you have to give you 0?
Because, yes, did everybody catch that? So when you would multiply, for example, A versus C, this is going to be positive, this is going to be negative, this is going to be positive, and this is going to be negative. And therefore, it's going to cancel out, right? So if you were to, essentially show that AD equals 0, right? This is saying that they're orthogonal. Okay? The other thing that you can do is, well, and so then what does that tell you about the contribution of S and P to the nature of those bonds?
It's 50-50.
Isn't it more P than S? It is 3P.
Oh, yeah.
Right? So if you did,
75 total.
we know that that's going to equal 1, right? So that if we multiply to all, and it doesn't have to be A, right? We could do, we could do C or D or B. Yeah.
Professor, it's not clear how the phi s actually cancels out, because those are positive for everything.
How they cancel out. Oh, so here, this would be positive 1/4. This would be negative 1/4, negative 1/4, positive 1/4.
Oh, we're treating them each as a value.
Yeah. Yes, because by nature, they're normal. Yeah. So then we know if we did that, it would be 1/4 plus 1/4 plus 1/4 plus 1/4.
Shouldn't the coefficient here be 1/4 then instead of 1/2?
No, because when you multiply them, right? So this is 1/2 phi s times 1/2 phi s is 1/4 phi s, which phi s is 1, right? Yeah.
Is this like just indicates the probability of the electron? Or what is this like?
What it represents is how much of the shape is governed by the S or the P. The question was, what the hell does this mean? And, and the answer is, how much of the contribution of this bond this is what your sp3 orbitals look like. This is what your p orbitals look like, and that's what your 1s orbital looks like. Does that look more like a p or more like an s? It looks more like a p, right? And remember, what our wave function is telling us is the shape and the distribution of that electron, right? So what these are telling you is how do these hybrid orbitals look? Yeah.
If you wanted them to cancel out, shouldn't you write like as a subscript or anything, SP3, YS, PX, PY,
Say it again.
So you said that if you multiply them together, the coefficients would cancel out. But to cancel them out, don't you need all the wave functions to be of the same type? So wouldn't you have to put them all subscript SP3?
They are. These are the same.
No,
Right.
it's not the question I'm having.
Are you the same in all in A? He's asking why is S labeled differently?
Why is S labeled differently?
Than in the wave function for A.
Essentially the same question.
It should be the same. These are the same, right?
In
Do you mind actually writing out the cancel movement?
So what do you want to show, that they're normal or that they're orthogonal? So they're orthogonal. So we would do Can I just write SX? Okay. That's A. Oh, you know what? Okay, yeah, I get what you're saying, and I did leave off a. Okay, good catch. Okay, so here, right, this is going to be 1/2 s squared. Or, I'm sorry, 1/4. Okay, good catch. Thank you. So now, when we do 1/2 s times 1/2 x, what do we know if we integrated an S and a PY? That it's 0, right? Because those are completely orthogonal. So anytime you get where this is always going to go to 1, and that's always going to go to 0. Yeah. How do we do? That's good. So what about, do I still have nitrogen up here? I don't. This is the most, a complicated-ish one. Yeah?
Can you explain how it represents what orbitals look like?
What this, like an individual, since these are all essentially the same, and these are all the same, right? These all have the same energy. This takes the components of the S and 2p, x, y, and z, and combines them in a way to describe the shape of this new orbital, which is completely unlike the S or the P.
Didn't you just say like each one is represented by like say 1, and that's how they cancel each other?
Yes, but this is a contribution of the S, P, D, and X. So for example, some of them have a lot more contribution. Some of them have more contribution from S and Y than X and Z, right? When I cross-multiplied them, that was just saying that this is a unique orbital relative to this, right? And when you square it versus itself, you're 100% guaranteed that there is an electron within that orbital. Yeah?
So on this energy diagram for nitrogen, what are the hybrids?
That's a perfect lead into molecular orbital theory. This, for nitrogen, it's sp. Actually, no, we can do that now. It's sp, right? Because you only had one p orbital that was involved in hybrid bonding. What we didn't show there was the contribution of the s orbital. And for
What would it look like? Like, what would the energy, like, you know how you split it over there? What would it look like here?
Let's get into that. That'll be the first thing we touch on Monday on Wednesday because that's a perfect lead. Be aware that in the notes there are these are the wave functions for an sp2 situation. So sp2 would be like this. Okay? Where you have one sp2 orbital, a sigma bond, and one pi bond. Okay? See you on Wednesday.